Here we discuss the hyperfine structure of ESR spectrum. We have already seen in the last class that the hyperfine structure of ESR lines is due to the nuclear electron spin coupling. So, which consists of two terms, dipole-dipole interaction term and Fermi contact term. So, therefore, we can say that the hyperfine structure of ESR lines is due to dipole-dipole interaction term and Fermi contact term. And also we have seen that for free radicals in solutions or for or the free or valence electrons in liquids and gases, that are the free radicals in solutions, the dipole-dipole contribution averages to 0. And also for free radicals in solutions, V crystal is also equal to 0. So, two terms will be zeros, and the Hamiltonian will be the sum of the other terms, which is given by minus cross h square by 2m del square plus V0 plus HSB plus HIB plus HF. So, here these two are there even in the absence of magnetic field. So, these are field free terms, and we neglect those terms, and we study the effect in the presence of the magnetic field. So, the spin Hamiltonian is approximated as Hs is equal to HSB plus HIB plus HF. So, HSB is equal to G into mu B into S dot B or B dot S. A dot B equal to B dot A, B dot S, and this HIB is equal to Gn mu n B dot I for a single nucleus present in the material. If there are more than one nucleus in the crystal or the material, then HIB is equal to sum over Gn mu n B dot II, sum over I. If there are two nuclei, then I goes from 1 to 2. If there are n nuclei, then I goes from 1 to n. So, the effect of I1, I2, I3, etc., In will be there. So, we have to use the summation symbol here. So, summation I over I Gn mu n B dot II. And we know that HF is equal to A S dot I, whereas A is the hyperfine splitting constant. So, this equation is true if there is only one nucleus present. So, if there are more than one nucleus, then there will be different I's, nuclear spins corresponding to each nucleus, and therefore we have to take sum over I, small I, A S dot II. So, if there are two nuclei present, the summation goes from I equal to 1 to 2. So, if there are n nuclei, the summation goes from 1 to n. So, we can see that the summation is also over the nuclei in the system. So, this term becomes summation over I A. So, S dot II can be written as II dot S. And we have forgotten to put a negative sign over here. This HIB is negative. So, this is the Hamiltonian in the presence of the magnetic field. But the second term, minus n over minus summation over I Gn mu n B dot II is approximately 2000 times smaller than the first term. So in the first approximation we can neglect this, and we can write the Hamiltonian as H is equal to G mu B dot S, the first term plus third term, summation over I AI. So A's will be different for different I's, because we have seen that this A depends on the nuclear G factor, so which is different for different nuclei. So therefore, A is 8 pi by 3 G n mu B mu n mod psi 0 square. So it's different for different nuclei, and so we have to use a subscript over A's also. So please put AI over here. So AI II dot S. So this is the Hamiltonian. Here we can see that the hyperfine splitting constant A is a constant for a particular spin. So as spin changes, the hyperfine splitting factor also changes, since it depends on the nuclear G factor. So as I changes, the nuclear G factor also changes. So now we can do different examples. So first of all, so this is the general equation, so we can apply this into different examples. So first of all, we consider the ESR spectrum of hydrogen atom. So here we have to consider the hydrogen atom in its ground state. So the expression for the Hamiltonian is this: H is equal to G mu B dot S plus summation over I dot S. But we know that the hydrogen atom has got only one nucleus, so we don't have to put the summation symbol. So summation symbol is required if we have more than one nucleus. So H is just G mu B dot S plus A I dot S. So we don't have to write AI because only one A is there, and treating this A I dot S as a perturbation, and also we can calculate the energy. So we know that the Hamiltonian acting on the wave function is energy times the wave function. So the energy can be easily found out from the Hamiltonian itself by substituting for the dot product. B dot S is actually B S cos of angle between them. So the corresponding energy is equal to G mu B into S into cos of angle between B and S plus A I S cos of angle between I and S. So this is equal to G mu B S into cos of angle between B and S is MS by root of S into S plus 1 cross H. The cross H terms cancels, and this root of, so actually we have a root of S into S plus 1 over here. We have approximated it as S. So cancelling this, we have this term as G mu B MS, and this one A I S. So we know that the angle between I and S is the product of angle between I and B and the angle between S and B. So the angle between I and B is ms by S. So this is actually root of S and S plus 1. We don't substitute this because this is already written as S over here. So this cancels, and here it is mi by I. So this S and I cancels, and we have A ms mi. So we have already studied a similar term in the case of Paschen-Back effect. So this is analogous to that, and we can see that the energy depends on the quantum numbers ms and mi. So we can write E as a function of ms and mi. So we can write E as ms and mi as subscript to E. So we know that for hydrogen atom I equal to half, and mi can have two values, minus half and plus half. And also for hydrogen atom there is only one electron, and whose spin is S is equal to half, and ms is plus or minus half and plus half. So we have two values, possible values for mi, and two possible values for ms, and therefore we have four combinations, 2 into 2, 4 combinations. So this energy can be found as E half comma half. That means ms is half, mi is half, is equal to G mu B by 2 plus A by 4. So when ms half and mi minus half, we get E half minus half. So that is again G mu B by 2 minus A by 4. So next combination is ms minus half and mi plus half, E minus half plus half. So then the energy is G minus G mu B by 2 minus A by 4. And we have the fourth combination, that is ms is minus half, mi is also minus half. So we have four combinations, minus G mu B by 2 plus A by 4, minus half into minus half. So A by 4. So these are the four possible values of energy. Now the selection rules of ESR are given by delta ms is equal to plus or minus 1 and delta mi is equal to 0. And we know that every energy level split depending on the value of its ms and mi in the hyperfine structure of hydrogen atom. So we can see that suppose we have a energy level like this, and due to magnetic hyperfine interaction, so it splits according to its ms value. So there is a specific energy for ms is equal to half, and another energy for ms is equal to minus half, and each of this level again split according to the value of mi. So from this expressions we can see that ms equal to plus half has got a greater energy, because when ms is minus half, this is negative. So we will draw a diagram such that ms equal to plus half has got greater energy than ms is equal to minus half system. So now when ms equal to plus half, so which one has got greater energy? Half. Then only this is plus A by 4. So this is mi equal to half, and the lower energy level is mi is minus half. So when ms is minus half, so there are two combinations. So out of this, the greater energy is this, because first terms are similar. Second term is minus A by 4 and plus A by 4. So this has got greater energy. So So for ms is equal to minus half, mi minus half has got greater energy. So here the upper energy level correspond to mi equal to minus half and lower energy level correspond to mi equal to plus half. So now the selection rules are given by delta ms is plus or minus 1. That means ms should change by plus 1 or minus 1 and delta mi is 0. That means mi should not change. So the transitions are such that delta ms is plus or minus 1 and delta mi equal to 0. So these are the allowed transitions and all other are forbidden. So the transitions will take place such that ms is plus 1 to minus 1. So ms half to ms minus half, there will be transition. ms ഹാഫിൽ നിന്ന് ms ഹാഫിലേക്ക് ട്രാൻസിഷൻ ഉണ്ടാവില്ല. അതുകൊണ്ട് ഇവിടെ നിന്ന് ഇങ്ങോട്ടൊരു ട്രാൻസിഷൻ ഒരിക്കലും ഉണ്ടാവില്ല. ഇതിൽ നിന്ന് ഇതിലേക്ക് ട്രാൻസിഷൻ വരാം. അപ്പൊ അതിന്റെ miയുടെ സെലക്ഷൻ റൂളും കൂടെ നോക്കണം. ഡെൽറ്റ mi ഈക്വൽ ടു 0. അപ്പൊ mi ഹാഫിൽ നിന്ന് mi ഹാഫിലേക്കൊരു ട്രാൻസിഷൻ. And mi minus half to mi minus half, another transition. So there are only two lines that corresponds to the transition delta ms plus or minus 1 and delta mi equal to 0. So now we can see that this line has a lesser energy compared to this line. And we can find the energy of each line as the energy difference between the levels. So the energy of this line is equal to the energy corresponding to the initial level minus the energy corresponding to the final level. So this has an energy, so equal to E half half minus E minus half half. So this corresponds to this energy. And this one has got an energy E half minus half minus E minus half minus half. So from figure itself, this energy is greater and we can find out the energy of each line as the energy difference. So we already found E half half, E half minus half, E half minus half and E minus half plus half. So substituting those values, we can see that E half half minus E minus half half is equal to G mu B by 2 plus A by 4 minus of minus G mu B by 2 minus A by 4. So the minus minus will be plus and for A by 4 also minus minus will be plus. So G mu B by 2 plus G mu B by 2. 2 times G mu B by 2 is G mu B and A by 4 plus A by 4 twice A by 4 which is A by 2. So the energy of that line is equal to G mu B plus A by 2. So let nu1 is the frequency of that line, then H nu1 is equal to G mu B plus A by 2. And you can find out the corresponding frequency by dividing both sides by H. So nu1 is equal to G mu B by H plus A by 2H. So this is the frequency of the first line, the line having greater energy in the ESR spectrum of hydrogen. So now we can find the energy of the second line. So that is equal to the energy difference between the starting level and ending level. So this line starts from this level and then here. So the energy difference between those two gives the energy of the spectral line. So that is equal to E half minus half minus E minus half minus half. So substituting these values, we can find that it is just G mu B minus A by 2. Please verify this. So there we have this energy minus this energy. G mu BB by 2 minus minus. So that will be plus. So twice this, that is G mu BB. So minus A by 4 minus A by 4. So that is equal to 2 times minus A by 4 minus A by 2. So that is the energy of the line. So this has got a lesser energy than the first line and the corresponding frequency. So this is equal to h nu 2, which is G mu BB minus A by 2. So nu 2 is G mu BB by h minus A by 2h. So we have two lines on the ESR spectrum of hydrogen atom, which is due to the hyperfine structure. H nu 1 is equal to G mu BB plus A by 2, and H nu 2 is equal to G mu BB minus A by 2. So those lines are separated by an energy equal to A. So the energy difference between these two lines is G mu BB plus A by 2 minus G mu BB minus A by 2. So we have two lines. So the separation between these two lines gives the hyperfine splitting constant A. So from the experiment of finding the spectrum of ESR spectrum of hydrogen atom, we can determine the hyperfine splitting constant of hydrogen. So that is nothing but the separation between the two lines and the spectrum of hydrogen atom. So now we consider a 1 electron system coupled to a nucleus having spin I equal to half. So consider a 1 electron system coupled to a nucleus of spin I equal to 1. So an example for this is a deuterium atom. So we know that in the case of deuterium atom, so the nucleus is a deuteron whose spin is I equal to 1. So deuteron is the isotope of deuterium, is the isotope of hydrogen, and its nucleus contains 2 neutrons and 1 proton. So it is having a spin I equal to 1, and in the atom there is only 1 electron. So here also we can see that the dipole-dipole contribution to the hyperfine is assumed to be 0, and the total Hamiltonian has only two main terms, which is equal to G mu BB dot S plus summation over AI II dot S. So here also we have neglected the middle term, which is the nuclear Zeeman energy term. So the corresponding energy is equal to G mu B into S into cos of angle between B and S, that is ms by S. So this S and S in the denominator will cancel, so as before. So G mu BB ms the energy due to this term. So we don't have to put the summation symbol since there is only one nucleus. So A into I dot S is sufficient. The corresponding energy is A into I into S cos of angle between I and S. So the angle between I and S is the angle between I and B multiplied by the angle between S and B. So A into I into S, ms by S, mi by I and S cancels. A, mi, ms. So here also ms can have two values, plus or minus half. So we know that ms can have only two values, and I here is 1, and therefore mi can have 2i plus 1 possible values, minus I2 plus I, minus 1, 0, 1, 3 possible values. So therefore there will be 6 different combinations, since ms has got 2 combinations, 2 values, and mi has got 3 values. So total 2 into 6 combinations will be there. So please find out the energy of all this. E half minus 1, E half 0, E half plus 1. These are ms values and these are mi values. So similarly, ms minus half, E minus half minus 1, E minus half 0, E minus half 1. So substituting ms and mi, please find out the 6 values and accordingly plot the energy levels. So this is an assignment for you. And find out the energies of the lines. So these are the energies of the levels. So a line is produced when there is a transition from one level to other level, and the transitions are in accordance with the selection rules. So the selection rules are again given by delta ms is equal to plus or minus 1 and delta mi equal to 0. So while plotting, we can see that there are 6 levels. So ms half combinations has greater energy than ms minus half combinations. So out of this, mi can have 3 values. So mi equal to plus 1 has got maximum energy, mi 0, mi minus 1. So similarly, ms minus half has 3 mi values, and out of this the maximum energy is for mi minus 1. So you have to remember that. So show that this has got maximum energy. Using the same procedure, we have defined the Esr spectrum of hydrogen atom. So this is 0, mi 0 and mi 1, and the transitions occurs according to delta mi equal to 0. And delta ms is plus or minus half. So delta ms changes by either plus 1 or minus 1. So in this case, it's half to minus half plus 1. So this is satisfied. So in between a transition half and half ms half and ms half ms half and ms minus half when mi does not change during the transition. So we have 3 lines, mi1 to mi1, mi0 to mi0, and mi minus 1 to mi minus 1. And you can find out the energies of those 3 lines by finding the energy difference between the corresponding initial and final levels. So this is also an assignment for you, and I will just write the final results, and we can see that there are 3 lines. So their intensities are equal, but the separation is equal to the hyperfine splitting constant A. So these are the energies. So we can see that there are 3 lines, and the separation between 2 adjacent lines is equal to the hyperfine splitting constant A. So the separation is also A. So here we get 3 lines which are separated by a distance equal to the hyperfine splitting constant. So we have seen that in the case of hydrogen, when the spin is half, we have 2 lines separated by hyperfine splitting constant. And in the case of deuterium atom, I equal to half, or any other atoms with I equal to 1, and that contain an unpaired electron. If I equal to 1, there are 3 lines separated by the hyperfine splitting constant. So for a particular value of I, there are 2i plus 1 lines. So when I equal to half, 2 into half plus 1, that is 1 plus 1, 2 lines are there. So when I equal to 1, 2 into 1 plus 1, 3 lines are there. So we can say that whenever an unpaired electron interacts with a nuclear spin I, then the number of hyperfine components expected is 2i plus 1. So if an arbitrary nucleus with spin I interacts with an unpaired electron, then there will be 2i plus 1 lines in the ESR spectrum. So for example, if I equal to 3 by 2, then there will be 4 lines. If I equal to 2, then there will be 5 lines. Okay, thank you.